Hi, this is Chris Jobling, and this is the pre-class presentation for the lecture on continuous system equivalence, which we're going to do on Thursday this week. So what I'm basically going to talk about today is the case where we've designed a control system or some continuous transfer function in the S-plane, perhaps using root locus methods or frequency response or whatever, and now we want to put that design into implementation using digital controller, a computer. And what we want, of course, is for the digital system, given that it is taking sample data rather than continuous data, that it behaves dynamically and steady state the same as a continuous system with the equivalent transfer function. And really we're looking for a digital system that has the same input-output behavior as the continuous system, and we call that a continuous equivalent. These are the topics I want to cover briefly in this pre-class presentation, and we'll do some examples actually in the class. But basically I want to first of all talk about how we represent S and Z, how they're related to each other, and then I want to go on to talk about equivalence, or ways of producing equivalence. There are a number. These are the ones that I want to cover. The so-called zero-holder equivalent, which is a transfer function basically that would have the same input-output behavior as if the original system was sampled. Then the Tustin bilinear transform, which comes around by basically approximating the integral operator using numerical integration, and then a couple of the match pole zero equivalent, which basically uses the relationship S to Z to basically put the poles in S at the same equivalent locations in Z, and a variation of that which we need to use in some situations. So quite a lot to get through. I don't want to take too long over it, so we'll possibly go fairly quickly and maybe say a little bit more in the sessions themselves. This is the system that I want to basically look at. So we have a system. This is the delay operator here, and we want to basically consider what the relationships are, input and output relationship between these two systems. So this is the input, this is the output. And if we just take the case of a continuous system sampled, then if we sample v of t, we get the sequence v of k, and that's delayed by this operator to give us the delta v of k. And we can take the z transform of that. The z transform of v of s is v of t is v of s, and then v of z is the equivalent of this transfer. So this transforms to this transforms to this, and then the delta operator itself transforms to the operator z minus 1, and so this there is the equivalent of the transfer function. So if we then move on to the next slide, we can look at this a different way. We can consider what might happen if we were to take a continuous time delay. So v of t now is time delayed by t. The operator there is v t minus t. If we sample that, we get the sequence v of k. So again, if we transform this, the transform of v of t is v of s. The transform of time delay is e to the minus st. So the result is the Laplace transform of vt minus t, which is equivalent to z delta vk. So those two relationships are similar to each other, and we can basically then use that relationship here to say that okay, if what I said previously was true, then z to the minus 1 is the same as e to the minus st. So z is e to the st, and if we want to find s, then s is 1 over t times the natural log of z. And so these relationships are precise relationships that relate the z operator to the transfer function operator, taking into account that basically this is unit time delay. So z minus 1 is a delay of 1 period in the system. So let's look at some methods then of getting that continuous equivalent. The first one we want to do is what's called zero to hold equivalent. So basically we take our initial signal v of k, we pass it through a transfer function, and we get the continuous function v of t. And we do this by essentially holding the value of v of t, what it was at the kth instance, for the period of the operation. It's easy to see this from a picture. So here is a typical picture. If I take a pen here and just consider what happens here, that's kt. So that's v of k when t is equal to t, and then we basically hold that value for that period there, which is k plus 1 times t. So essentially for that one unit step there, we're generating a piecewise continuous function where the starting value is the value of the sample function at the time at which the sample is taken, and that's held for the period until the next sample is taken, and then we move on, as you can see by this, get a stepwise continuous signal. So if we model that mathematically, what we need to do is first of all consider the kth pulse. So that starts at kt and ends at k plus 1t, and its value is vk, the value of the sample value at the start of the period. And we can model this by taking two step functions and adding them together. So if we take a step function like this, take a pen here, this step function here, that's basically is equal to vk, the amplitude is vk, which is of course this value here, and then e to the t minus kt is the time delayed unit step, which is, if I take a different colour, this value, this here is that function. So the height is equal to vk, and we're multiplying it by this unit step function. And we do the same thing for the downgoing pulse. There's a unit step in red, and the actual value of vk in green is the value of that value there, the height of that function. We call this a gating function. And so if we write that down in this form, so pt, that's the pulse function, is equal to this equation, which we can simplify by taking vk out to the brackets. It appears in both terms, so vk e to t minus kt minus epsilon t minus k plus 1t, where epsilon is a unit step function. And so for a sequence, we've got the sum of all possible pulses like that. So we go from 0 to infinity of all the values that we could, and then we can take the transform of that. So if we take the transform of the unit step, it's 1 over s. If we take the transform of the delayed unit step, it's 1 over s times e to the minus kts, and then the next one is 1 over s e to the minus k plus 1 ts, and we're taking the sum of all those possible values. We take out the common terms, the terms that don't involve k, then we end up with this here, 1 over s times 1 minus e to the minus ts, and then the rest of the summation is the value there, vk e to the minus kts. And this, of course, is the z transform. The z transform of vk is vk z to minus k, so that's the z transform. And this is the 1 over s. E to the minus ts is z to the minus 1, so we can replace e to the minus ts by z to the minus 1. And we're left with this mixed transform, 1 over s, which represents the step function, z minus 1 over z, which represents the delayed step, and then v of z, which is the transform of the z transform of the sequence itself. And this gives us a transfer function that represents the zero to hold. So we can basically say the transfer function is of the zero to hold is a mixed transform 1 over s times z minus 1 over z, and we feed v of z into it and we get v of s out of it. So that's the way this thing works. So it's equivalent really of running the system in either of these two ways. We can take u of s and sample it to get u of z, and then we can feed u of z through h of z, and that will give us y of z. The dotted lines represent the discrete signal. Or, alternatively, we could take u of z, push it through a zero to hold, then feed the zero to hold through h of s, get y of s, and then if we sample y of s, we would get the equivalent y of z. So these two systems are equivalent to each other. They give the same output for the same input in the digital consideration. So we can use this like this. If we have a y of z, we want to produce a h of z, then what we do is we basically take the z transform, divide by s, multiply by z minus 1, and get this relationship h of z, z minus 1, z times h of s over s. Okay, so that's how we basically proceed from that. And we'll show you an example of that in the lecture. We will take this system, a over s plus a, and find the zero to hold equivalent. We'll do that in the lecture. If you want to look at that now, it's in the notes. So that's the first method. The second method is based on numerical integration. We could, theoretically at least, take this relationship that we derived initially, s equals 1 over t times the natural log of z, but we can't use this as a substitution because we won't get a rational function. So we need an approximation to it, and the approximation we use is basically the integral. So we have a t of z equivalent to t of s, and let's assume the t of s is s. Then what we perhaps, to get at that, what we can do is we can basically look for a transfer function for 1 over s, or the equivalent transfer function of 1 over s. So we're basically taking 1 over s and looking for its equivalent z transform. And we do this by integration. So essentially the value of u of z, because this is an integral, the y of z will be the integral of u of z over time, and so basically it's going to be the area under this curve is going to give us that thing. If we could calculate that precisely, then we would get the right answer. But what we do is take a simplified model. Basically we break it up into pieces, look at the nt minus teeth and the n-teeth version. So we're looking just at the integral between over one sample period, and of course that value u is nt minus t and unt is there. And so a number of ways we can approximate that. We could take, for example, just rectangle here shown in blue. That would be t times unt minus t. So t is the width and unt minus t is the value at the start of the integral cycle. And usually it's not a particularly good underestimate in this particular case. And that's called the forward rectangular approximation. Or we could take it from the back end and take a larger scale. In this case it would be an overestimate of the size. It would then be t, u, and t. But probably the best compromise between those two would be the trapezium here. And the trapezium's area is t over 2 times unt minus t plus unt. So we can basically take that expression and form the z transform. So the nth value of y is going to be approximately the previous integral value plus this new estimate of the current sample, and if we take z transform of that, then y nt minus t z minus 1 is y of z, unt minus t is z minus 1 of u of z, u of t of course is u of z, and ynt is y of z. So y over u, which is our estimate of the integral, is t over 2, 1 plus z minus 1, 1 minus z minus 1. And if we realise that's 1 over s, then s is going to be the reciprocal of that expression. So s is approximately 2 over t, 1 minus z minus 1 over 1 plus z minus 1. So we can basically say, let's use these two approximations then. Let's say s is equal to this, z is equal to that. This is called a bilinear transform, or Tustin's bilinear transform. And if we compare those two results, if we expanded that, then this expression here would expand to 1 plus st plus a half s squared t squared plus a quarter s cubed t cubed and so on. The actual expression z equals e to the st is 1 plus st plus a half s squared t squared plus a sixth s cubed t cubed. So you can see the two expressions are very similar up to the point, up to the second order term. So they are equivalent up to that term. They start to diverge after that. But it's a reasonable approximation, at least for the purposes of keeping it simple. Just for comparison, the forward rectangular approximation would give us this. It's only accurate really up until the second term, and then the third approximation is only accurate, even less accurate than that term. So, in our second example in the lecture, we'll look at how we can use Tustin's bilinear transform, that relationship, to determine a transfer function, for example 2. The third approximation is perhaps the simplest of all to actually use, and that's basically takes the idea that let's assume that when we do the sampling operation, that the poles in d of s will become pole zeros of d of z, just by using the mapping z equals e to the st. And so we can use this to produce a relatively simple transformation. So what we do is we map the finite pole zeros to pole zeros of d of z using that transformation. We then add any zeros for infinite zeros in d of s. These will get z equals minus 1 because that's basically equivalent to an infinite pole in an infinite zero in the z domain. And then we match the DC and or low frequency gains so that they both have the same DC, two transfer functions have the same DC relationship. So we will show you how we use that operation in this example. This is an example where we have the same number of pole zeros. And then the fourth example, we have one more pole and zero, so we need to add this extra zero at z to minus 1 in order to solve it. And if we implement an MPZ approximation, we're going to basically get transfer function. This is for the first order case, something like this. So this is the transfer function. This is how it would expand. Y of n is b y n minus 1, k un alpha un minus 1, and these values are essentially past value of output, past value of input, current value of input, current value of output. And so we get y of n computed based on the previous value plus the current value of input and the past value of input. But of course we can't, it's impossible to compute y of n immediately. It takes time to do the computation. So this only really works if the computation rate is much less than any significant dynamics of the sample system and a small fraction of the sampling time. Otherwise there'll be a significant delay, and that delay can destabilize your system. So there's a modified MPZ, match pole zero equivalent, which is used if we can't computation time. If we don't, in this case we will allow a0 infinity, so that the order of the numerator is always going to be one less than the denominator, and this assumes that only pass values appear, and we'll show you that in example 5 during the class. So that's our introduction to the class that's coming on Thursday. This is a summary of what we've done. We've basically given you the actual relationship between S and Z, which will be useful in the next class, and then we've looked at 4 ways that we can convert an h of S into an h of Z: zero-order equivalent, Tustin bilinear transform, match pole zero equivalent, modifier match pole zero equivalent. And we'll do examples to illustrate all of these. Those are the things you'll need to know for the exam to come. And we'll also demonstrate how Matlab does this. Matlab basically implements most of these as well, and we'll show you how we can use Matlab to generate those transfer functions. And we'll also perhaps have a look at the relationships between them in the class on Friday. So, thanks for watching. I hope that's been useful, and I hope you're ready now for the session that we are going to have on Thursday. Well, I'll see you then. Thank you very much.